Good afternoon and welcome to Monash University's Virtual Open Day. In this talk, I would like to introduce you to a discipline of science called Earth Science, a branch of physical sciences, the study of non-living things. Earth Sciences focuses on the Earth and its nearby neighbors, its atmosphere, rocky composition, its environments and oceans. My name is Ruth and I'm a lecturer here at Monash. I'm an oceanographer, an earth scientist interested in how sea level rise and storms impact coastal habitats and infrastructure. Earth science is a fantastic endeavor. Whether you are fascinated by mountains, ice sheets, climate, rocks, fossils, oceans, and life-sustaining environments, or are just seeking to broaden your understanding of how biology, chemistry, and physics are expressed on Earth's template. Many of humanity's greatest challenges, such as climate change, pandemics, natural hazards, mass extinction, resource scarcity, droughts, and bushfires, are rooted in earth science, as you will see later in this presentation. A scientific understanding of our planet and these issues enables us to better advocate for change and to create solutions. Earth science has consistently provided a path to meaningful employment in environmental consultancy, resources, weather forecasting, risk analysis, natural hazard management, scientific research. The list goes on. You can find a link at our booth, which is the Earth, Atmospheric, Environmental, Geographical, and Climate Science booth. Some of these jobs are lucrative. Most of them are better paying than most STEM graduate roles. But most importantly for me, they make the world a better, smaller, more sustainable place full of wonder and exploration. So come on and explore the planet with us in our first year sequence, EAE 1011 and EAE 1022. This first year sequence leads into two majors, one of which is the atmospheric science major, and the other is the earth science major. The earth science major is a broad major and has a number of specializations, including the geosciences and the environmental and climate science. If you take an earth science major, you can keep it as broad as you like by combining units between these two disciplines. If you're interested in geography, at Monash we teach geography in two main pathways, either as a major of science in the form of geographical science, or as a major in the Faculty of Arts, which is the human geography component. Regardless of which pathway you choose, you will take units across the two faculties. Starting from first year, if you're doing a geographical science major, your first year sequence will be ATS 1310 and EAE 1022. So what do you study in EAE 1011 and EAE 1022? You'll study the scientific background to climate change. You'll learn about the weather extremes, bushfires, and other natural hazards. You'll explore the makeup of the Earth and how it evolved over the past 4.5 billion years. You'll get involved in global issues like food and water security. You'll expand your knowledge of Australia's environments, oceans, geology, and climate. You'll develop highly sought skills in mapping, mineral identification, environmental management, data analysis, and introductory research skills. Maps are one of the most common forms of communication, and we'll teach you how in EAE 1022. And you'll join a vibrant network of hundreds of other students through participation in field camps, laboratory practicals, and group work. I will leave you with quotes from our latest cohort of EAE 1011 students. For more detailed information on these different disciplines, please continue watching this video, where some of your lecturers will describe future careers, your education at Monash University, and the research questions and global challenges they address in environmental, climate, geological, and Antarctic science. I look forward to seeing you in our first year EAE 1011 and EAE 1022. Myself and my colleague Ian will be available at the live Q&A at the end of this presentation and at the booth from 10 to 2 today and tomorrow. Thank you.
G'day, I'm Adam. I'm a biogeochemist in the School of Earth, Atmosphere and Environment at Monash. And that means that I study how things cycle through the environment. My particular focus is on water and sediment and how things cycle through water bodies such as lakes and streams and rivers. This footage comes from a recent field trip. It's part of one of my projects studying the fate of nitrogen in Victoria's estuaries. And the problem is this: when too much nitrogen flows into an estuary, it usually leads to algal blooms. And you might have seen things like this if you've been to Port Phillip Bay or the Gippsland Lakes during problem times in the last few years. Now fortunately, the microbes that live in the muddy sediments below our estuaries are really good at reacting nitrogen. But there are two main types of reaction: a removal reaction that turns the nitrogen into harmless nitrogen gas, but also a recycling reaction, which keeps the nitrogen in the estuary and sometimes makes the problem much worse. And this project is working with groups like the EPA, catchment management authorities, and the Department of Water to understand what conditions make the removal reaction, or the recycling reaction, more dominant. And to do this, we need to visit some beautiful estuaries like this one, and collect some sediment, and bring it back to Monash to learn its secrets. Our estuaries are really beautiful, and I hope that this research can help us to understand how they work so that we can keep them that way.
Hi, my name's Kelly. I'm an honours student in the School of Earth, Atmosphere and Environment. I've just collected a whole bunch of sediment cores like this one from this estuary here, and I'm going to look at how the chemistry of nitrogen changes within these cores when burnt bushfire sediment is added to them.
Hi, I'm Sarah Tinsley, and I'm currently doing an honours year with Vanessa looking at arsenic from calcined sands in old mine tailing sites. I started studying in soil science because I liked the variety of stuff that you could learn from just a little bit of soil.
Hi, I'm Vanessa. I'm a soil scientist and an academic in the School of Earth, Atmosphere and Environment. So what do environmental scientists do in their day-to-day job, and where do they work? Environmental scientists work across a range of different organisations in the public, private and not-for-profit sectors. So that means environmental scientists work in government organisations, private companies and non-government organisations. Environmental scientists are also multidisciplinary as well. In terms of their day-to-day tasks, they include developing management plans or policies to minimise the impacts of industrial, agricultural or urban processes on the environment. They also participate in community education and educate the community on environmental issues. They assess, investigate and develop environmental guidelines for regulatory bodies and also undertake environmental research. Environmental scientists also develop sustainable practices and incorporate them into an organisation's operations. In terms of areas of expansion for environmental scientists, expanding areas include the assessment of contaminated land and contaminated water and the remediation of these sites. So environmental scientists look at remediating mine sites such as the coal mines in the Latrobe Valley, industrial areas such as old petrol station sites, of which there are many around Melbourne, and also on infrastructure projects such as the Metro Tunnel and the Westgate Tunnel. But don't just take our word on this. The Australian Government has produced a Jobs Outlook which looks at career prospects and employment prospects for a range of different careers. They describe environmental scientists as scientists who develop, study, implement and advise on policies and plans for managing and protecting the environment, flora, fauna and other natural resources. And they also project strong future job growth in this particular area. A quick look online in terms of what companies and where environmental scientists work include those in the private sector or environmental consultancy sector as contaminated land consultants. In the private sector, working as a sustainability manager, so incorporating and developing sustainable practices within an organisation. Local councils also employ sustainability officers and environmental scientists, as do water utilities companies. So South East Water is a water utilities company and they're also looking for an environmental scientist. And in terms of graduate level positions, there are also a range of graduate programs available for environmental science graduates as well. So how do you become an environmental scientist and what do you study in the School of Earth, Atmosphere and Environment to become an environmental scientist? Our school offers 3 majors in the Bachelor of Science and associated degrees. We offer the Environmental Science Extended major, the Earth Science major, and the Geographical Science major. If you're really interested in the multidisciplinary aspect of environmental science, then the Environmental Science Extended Major is for you. And that extended major has the Environmental Earth Sciences stream. That stream will incorporate aspects of earth and environmental science, biology, and chemistry. If you're really interested in understanding how the world works and want to delve into that in more detail, then the Earth Science major is for you. And within that, there's a physical environment stream. The first year sequence looks at an introduction to earth science, atmospheric science, and environmental science. On the other hand, if you love geography and you want to understand how humans and society interacts with the natural environment, then the Geographical Science major is for you. The first year sequence is a combination of a human geography unit and a physical geography unit. These three majors will provide you with a foundation to allow you to explore in detail what you're really interested in as you delve into the deeper details of environmental science.
Come and join me on a journey through geoscience to learn more about why our discipline is crucial for a sustainable future. We need critical metals for the technologies required to cut carbon emissions in a sustainable energy future. Geologists are the scientists who will drive the discovery of these important resources, and they will contribute to environmentally responsible ways to extract them from the earth. Working together with other industries to find smarter solutions which need less of those minerals is another important aspect of our work. As long as humankind can remember, natural hazards have always been part of life. But the more we learn and understand about the mechanisms within the earth that drive these natural hazards, the more we can predict when and where they happen. This video, for example, shows how geologists are able to track earthquakes. The geoscience program at Monash is strongly focused on training problem solvers with a broad range of skills. Central to geology are the tools and techniques that we use to understand and interpret the materials, rocks and minerals that make up the Earth and other planets in our solar system. You will learn how we study the processes that shape our planet and about Earth's amazing and complex history over the past 4.5 billion years. But geology is not just all about rocks, minerals and fossils. Modern geoscientists use the latest state-of-the-art technologies and sophisticated methods to see deep inside the Earth and analyze the composition of tiny amounts of Earth and solar system materials, like this meteorite. You will use the insights gained from these tools to understand how the Earth works, how to explore for resources we need in the future, and how to improve our environment. As a geoscience student, you will also learn about how our planet's climate has changed over billions of years and how we manage other critical resources like groundwater.
Hi everybody, my name is Andrew McIntosh and I'm the head of the School of Earth, Atmosphere and Environment at Monash University. Today I'm excited to be talking with you about Antarctica, a place I'm passionate about and that I've had the privilege of visiting many times. Antarctica is the coldest, driest and most remote continent on Earth. It's probably best known to you for its penguins, but today I'm going to be talking about the ice sheet, which covers an area larger than Australia and is more than 4 kilometres thick at its centre. If all of this ice was to melt, it would fundamentally transform our planet's coastlines, flooding cities and in some cases whole countries. So the question is, what do we need to do to better predict the future of Antarctica and its ice sheet? Around 20 years ago, when I started out as a scientist, we thought Antarctica wasn't changing very much. We thought there was an approximate balance between the snowfall that was coming in and the ice loss at the margins. But as the 2000s progressed, things really started to heat up. What we're focusing on here is the change over a number of years. The map to the right shows the cumulative mass pattern. Reds are for areas of ice loss and blue for areas of ice gain over the entire Antarctic ice sheet. As time goes on, and in particular after 2007, a huge red spot develops over West Antarctica. We also see areas of mass gain due to increased snowfall, but they're not nearly enough to offset the loss. It's this creeping, growing, giant red spot, which is due to the rapid acceleration of ice, thinning of the ice sheet, and retreat of its major outlet glaciers. And all of this has been driven by warming of the ocean. The Intergovernmental Panel for Climate Change, of which I'm an author, has indicated that mass loss in West Antarctica could be the start of an unstoppable and irreversible feedback. This could result in the entire loss of the West Antarctic ice sheet in coming centuries. Parts of the East Antarctic ice sheet directly to the south of us here in Australia are also potentially vulnerable. And if the West and East Antarctic ice sheets together start to disintegrate, then we could get metres of sea level rise over coming centuries. To learn if this is really going to be the case, we need to do a few critical things. The first thing we need are longer observations of the ice sheet. Current observations from satellites only go back a few decades, and this is not nearly long enough to know whether the current behaviour is unusual. The second thing we need are better observations of the bedrock beneath Antarctica and of the oceans surrounding it. The oceans have been warming, but is that the same everywhere? How does that affect the ice sheet? We don't really understand it yet. The last thing we need, and this is really critical, are more accurate computer models of the ice sheet. Computer models are amazing. They allow us to imagine the future and calculate the sea level contribution from Antarctica. These models need to take into consideration our greenhouse gas choices, because ultimately it's going to be our decision as humans that makes the difference about how the Antarctic ice sheet changes. I'm now going to pass over to my awesome colleagues who will talk about each one of these topics in turn.
The Geological Past provides valuable insight into how the Antarctic ice sheet is changing today and how it will change into the future. Rocks and sediments record past times when the ice sheet grew and retreated, allowing us to better understand how ice sheets respond to changes in the climate. We are particularly interested in when, where, and how the Antarctic ice sheet retreated after the last ice age. And to answer these questions takes us to Antarctica. We fly south to the great white continent of Antarctica. We set up camp, consisting of polar tents and an igloo toilet, in the mountains alongside fast-flowing outlets of the ice sheet. Our aim is to collect rock samples, ice-free bedrock surfaces and perched cobbles, often using power tools, hammer and chisels. Each sample can tell us when the ice sheet surface lowered to expose that rock surface. By collecting rocks at multiple elevations above the modern ice surface, we can produce a timeline of past ice sheet thinning. We then return with our rock samples, which we then process in the lab.
Modern observations tell us about the current state of Antarctica, including how it's contributing to sea level rise. And they can also tell us about the processes that are driving change. We know that the ocean is the biggest driver of current ice melting and loss from Antarctica. Ocean melting is therefore one of the most crucial measurements we collect when we go to the field. As the ocean melts beneath the floating ice shelves that encircle Antarctica, the ice that's grounded on bedrock upstream can actually speed up and flow faster into the oceans. These days we have satellite records, such as NASA's MEASURES dataset, that can show us how fast the ice is flowing. From these data, you can really see that the patterns of ice flow in Antarctica look a lot like water flow on land, from small streams into large tributaries that flow into the ocean. These patterns of ice flow are strongly guided by the bed topography below, which is another very important quantity to measure. Models are tools that we use to understand the environment, the processes that are operating, and how they might change in the future. The ice sheet models that we use are made up of mathematical formula that we translate into computer code and that integrate real-world data, such as ice speed and thickness, to build up a picture of the current state of Antarctica and how it might change over time.
Many people ask me, how do I become an Antarctic scientist? How do I become a glaciologist? The answer is that there are many different pathways, but you can follow them all in our school. If you're a geographer, great. A geologist, fantastic. A meteorologist, a mathematician, or a physicist, come and join our ice sheet modelling team. What about geochemistry? Well, we're building a new lab for you right now. So no matter what your background or pathway, there's a way that you can get into Antarctic science if you're passionate about it. And I'd love to support you and see you in our school.
It's Christian Jacob, and I'm here with Nigel Tepper and Julia Arblaster. And the three of us are all staff at the School of Earth, Atmosphere and Environment, and our general background area is atmospheric science.
How do we predict the future? How does it work?
Yeah, one of the fascinating things we do in atmospheric science is we look into the future. Not many people have the privilege of doing that. And of course, the running joke is that the crystal ball was a bit cloudy today, and so the weather forecast wasn't quite as good. But actually, we don't use crystal balls to make these predictions. We use modeling, and you hear a lot of about modeling right now, don't we? We hear COVID-19 modeling, and before that, we often hear about economic modeling and what the growth rate is and what the exchange rate will be. Turns out the models we use to make weather and climate predictions are quite different from a model that predicts COVID, in that rather than looking at past data and extrapolating from that past data into the future, we actually start with what looks like Egyptian hieroglyphs to most of you, I presume, a bunch of equations, mathematical equations, but they're actually quite familiar things to all of you who've done physics in high school. There's Newton's second law in there, there's the law of energy conservation, and so on. What we do is we take those equations and then we divide the Earth up into boxes. That's this picture in the middle, right? So, and then we calculate the temperature, the pressure, and all the things for each box. Turns out to be one of the most computationally expensive things you can cook up. And so to do it, we need a supercomputer, not just a little computer or a computer. No, we get supercomputers to do it. Ours sits in Canberra at the National Computational Infrastructure, and it's a very powerful computer. And all these things together, we can produce a forecast for the weather every day. And so here's one for tomorrow, Saturday and Sunday. Or we can also run these models longer into the future, and we can ask if the composition of the atmosphere changed, if we had more CO2 in the atmosphere, how would things like the global mean temperature change? And here's a result of this. And we have result from two different assumptions. The blue line is if we don't change the CO2 in the atmosphere much further than where we are right now. The red one is if we continue business as usual. And what we can see in one scenario, the Earth will be about 1 degree warmer by 2100. In the other one, it will be 4 degrees warmer. And it's quite an amazing thing to be able to do this, actually. And you can see how atmospheric science, just in this little slide, has mathematics and physics in it, has computational science in it. And then, most importantly, well, once we figured out it's going to be 4 degrees warmer, then what happens, Nigel? What impacts do we expect from, a 4 degree warmer world?
The work that we've been doing in this broad area began back about 10 or 15 years ago, where we did some of the early work for the Department of Health in Victoria on heat-health relationships. And one of the things we did was we looked at all of the mortality data over about a 25-year period on a daily basis. And we looked at the climate and the weather characteristics of the days, and we looked at what the mortality anomalies were on each day compared to what we would normally expect. And in the end, we found that a very simple relationship between temperature and mortality actually described a lot of what was going on in Melbourne and Victoria. And this has become the basis of the Victorian heat warning system. So just looking at this diagram, we can see that an average, note this is mean daily temperature. So it's yesterday's maximum or this morning's minimum. So over here we see that if we have a 40 degree day followed by a 20 degree night, then we have a mean daily temperature of 30 degrees. And what we find is that there's very little impact of changing temperature all the way up to about 28 or 30 degrees. And then we have a threshold temperature above which people begin to die at increasing rates. And in fact, above that temperature, the death rate in this age group, above 64-year-olds, which includes me now, increases by about 17% overall. But the critical thing to note here is that just reducing those temperatures by a little bit can save lives. And that's really provided guidance for not only for heat health warnings, but it's also a target for heat mitigation. So a lot of the other work that we've been doing in the last 10 or 15 years, and we've had the help of postdocs and about close to 20 PhD students, is to look at what we can do to reduce city temperatures so that we can save lives and provide a lot more thermal comfort. So we've been focusing in particular on the role of water and green infrastructure That is things like increased tree cover and forest cover, green walls, green roofs, trees in the landscape, trees on the roadside, bioswales, increased water bodies, and so on and so forth. And what we've been able to do is look at basically at two scales. At the micro scale, we've been looking at ways of reducing air temperature and radiant temperatures to improve thermal comfort. So this is down here at the micro scale. And what we found is that we can reduce feels-like temperatures under heatwave conditions by as much as 10 degrees by providing more shade and providing cooling through evaporation, evapotranspiration. And then at that larger city scale, we can provide actual air temperature cooling of 1 or 2 degrees. And from the earlier work that we did on the sort of epidemiology of heat and health, we know that 1 or 2 degrees cooling on a 45-degree day or a 40-degree day is actually going to save lives. So that's pretty much where our focus has been in the last few years. So I guess that really we need to now think about what the opportunities are for students to actually come and join us to do some of this really interesting and we hope useful work on extremes, on modelling, and on adaptation to climate change. So perhaps I could throw the question over to the other two of you. What can we do here at Monash to help people with this?
So I think even this very short tour through our work has shown the breadth of the sorts of things you can do if you come and study weather and climate at Monash. You can do it in several ways. You can do it by studying meteorology, you can have a climate science degree, or you can study geography, and all of these connect you to these issues that we've discussed today. And I think for more information, I would direct the students to the brochures and also to the open day booths, which are online this year as well, thanks to COVID. Hopefully we'll see many of them around. What do you think, Julie?
Yeah, I think for those really interested in the topic, there's this our major in atmospheric science, but in reality, I think climate change is going to affect any job that people go into. So even just getting a taste for some of our courses, you'll learn a lot about how the climate is changing and how it might change in the future. And you'll learn skills that I think are really useful in many different careers. So data analysis, big data that we use. Our climate models run on supercomputers. So you learn lots of varied skills as well as learn about something fun.
If you're not sure.
Sorry?
Just jump in there and say, look, we've got opportunities in the school for people that come from all sorts of backgrounds. So I'm a physical geographer. So if you come more from the geography background, there's a place for you here. If you come from computing or mathematics or other areas of the physical sciences, it doesn't matter. There's usually a place for you in atmospheric science.
And if you're not sure whether this is for you, I recommend you take the first year units that the School of Earth, Atmosphere and Environment offers and see how you like them. Where in those units, you'll get a very broad overview of all the topics that are covered, including weather, climate, and its impacts. And we even offer you a first year unit, elective unit on climate change and its impacts specifically. And that's targeted at any student because, as Julie quite rightly said, climate change will affect all of you, no matter what your job will be, no matter where in the world you will be, climate change will be with you. So maybe on that note, we should sign off and thank everybody for watching this video.
Thanks for listening.
Thanks for listening.
Bye.
Thank you. Bye-bye.